A warm welcome to the fourth lecture on the subject of wavelets and multirate digital signal processing, in which we intend to build further the connection between signals or functions in L2R and vectors, and therefore, we wish to build further the idea of thinking of functions as belonging to linear spaces and characterizing them in a manner slightly different from what we were doing in the previous lecture. So, just to put our discussion in perspective, this is the fourth lecture on the subject of wavelets and multirate digital signal processing, and what we intend to discuss in this lecture is the following. Let me put down the points one by one. The first thing that I wish to talk about today is to think of functions as generalized vectors. This idea is going to be useful to us in many different contexts in this course. So, we need to understand this connection between functions or signals and vectors in depth. We shall spend some time on it today. Secondly, the connection between L2R functions, connection or connections between L2R functions and sequences. We wish to understand this in greater depth. So, what we are going to show in the latter part of this lecture is that one can intimately relate processing of a function to processing of an equivalent sequence, and whatever we are doing to try and gain information from or modify a function can be done by equivalently processing or modifying that sequence corresponding to the function. Let us then embark on the first of these two objectives now. You see, let us begin by asking what characterizes a vector after all. Let us take a minute and reflect. What characterizes a two-dimensional vector, for example? A two-dimensional vector is essentially characterized by two coordinates which are independent. We call them perpendicular coordinates. Actually, the idea of perpendicularity there is also intimately related to the idea of independence. So, for example, let me treat the plane of the paper as a two-dimensional space. So, the two-dimensional space corresponding to this paper. Well, let us take any vector on this two-dimensional space. So, let this vector be V, I am marking it as V. There are many different ways to characterize this vector. In fact, notionally an infinite number of ways, and one of those ways is to choose the following two so called perpendicular axes. So, we choose one axis like this and another axis like this, and choose a unit vector along each of them. So, I have say a unit vector, let me call it u1 cap along this axis, and another unit vector u2 cap along this axis, and then I could write v1 or I could write this just the vector v uniquely as say v1 times u1 cap plus v2 times u2 cap, whereby v1 and v2 characterize this vector v uniquely in this two dimensional space with respect to the coordinate system generated by u1 and u2. And there is an infinity of such coordinate systems. In fact, one infinity of such coordinate systems can be generated simply by rotating this coordinate system of u1, u2. It is very easy to see that if I take this structure u1, u2 and rotate it by any angle in this two dimensional plane, it would give me a new coordinate system. So, there is an infinity of orthogonal coordinate systems in two dimensional space, and in fact, there is also a relation between all these infinite orthogonal coordinate systems. Simple enough. And orthogonal coordinate systems are not the only kinds of coordinate systems for a two dimensional vector. So, for example, the same two dimensional space can be described by the following different coordinate systems. So, I will draw the same vector v. And it is perfectly all right to choose a coordinate system something like this. I could choose one coordinate like this and another coordinate like this. And of course, I could again have the unit vectors in these two directions, u1 cap so to speak, u2 cap, and I could express v in terms of u1 cap and u2 cap. Indeed, I could complete a parallelogram here. So, using the parallelogram law, I could draw a line parallel from the tip of this vector to this u2, another one parallel to u1 from the tip of the vector, and it is very easy to see that this dot dash vector here plus this dot dash vector here gives me v. So, let me highlight that dot dash vector. This vector here plus this vector here gives me v. Let me call this v1 tilde, and it is a vector, and let me call this v2 tilde, that is again a vector. Of course, we have v is v1 tilde plus v2 tilde, and it is very easy to see that v1 tilde as a vector is some multiple of u1, and similarly v2 tilde as a vector is some multiple of u2. Thereupon, I have v is some multiple of u1 plus some other multiple of u2. K1 u1 plus K2 u2. The only catch is determining K1 and K2 is a little more difficult than determining the constants in the previous representation. In fact, let me go back to that previous representation. I had this representation previously, where V is V1 U1 cap plus V2 U2 cap, and remember V1 and V2 here of course are constants and very easy to obtain, because I can simply obtain them by taking a dot product of V with U1 cap and V with U2 cap. So, in fact, in the sense of dot products, V1 is indeed V dot U1 cap, and V2, I mean V1 as a coordinate, not as a vector, V2 as a coordinate is the dot product of V with U2 cap. Simple enough. Such a simple relationship does not exist in this context. While we are not hard put to describe the process by which we obtain K1 and K2, it simply says construct a parallelogram. Expressing this analytically is a bit of work. So, it is definitely very clear from this example that an orthogonal or a perpendicular coordinate system has its advantages. It is always nice to have a perpendicular coordinate system in two-dimensional space to represent any two-dimensional vector. The same idea can of course be extended to 3 dimensions and then one could also conceive of more than 3 dimensions, 4 dimensions, n dimensions, and then in principle an infinite number of dimensions too. Now, there again when we talk about infinite dimensional situations, we have countably infinite and uncountably infinite, finer points, but for the moment infinite is difficult enough. So, infinite dimensional vectors in fact lead us to the idea of functions. Now, it is a little difficult to understand infinite dimensional vectors all at once. So, to progress towards infinite dimensional vectors, it is easier first to start from finite dimensional vectors of larger and larger dimension. And all that we need to do is to understand that what characterizes the dimension of a vector is really the number of independent coordinates that it has. For example, a 3-dimensional vector has 3 independent coordinates. A 4-dimensional vector would have 4, an n-dimensional vector n, and an accountably infinite dimensional vector would have a countably infinite number of dimensions or a countably infinite number of coordinates. By countable, we mean we can put the coordinates or the dimensions in one-to-one correspondence with the set of integers. So, we can talk about the 0th coordinate, we can talk about the 1th coordinate, we can talk about the -1th coordinate, the -2th coordinate, and so on and so forth. What are we talking about here then? If we talk about an infinite dimensional vector, we are in fact talking about sequences. So, we will build up the idea from there. So, here we are. Let us make a note of this. An infinite dimensional vector, or rather an countably infinite dimensional. Vector is essentially a sequence. So, for example, we have a sequence x of n, where n belongs to the set of integers over all the integers. Recall that this script z is a representation of the set of integers, and this is called the index variable. So, now we have a different interpretation for sequences. A sequence is like a vector, and each n is a different dimension of that vector. Okay? I think that is important enough for us to write down explicitly. So, a sequence is a vector. Each n is a different dimension of the vector. And once we have this analogy, then extending other ideas of vectors to this context is not difficult at all. For example, adding two vectors, simple, add the sequences point by point. Multiplying a vector by a constant, very simple, multiply each point of that sequence by that constant. What we would like to do now is to extend some of the other ideas of vectors that we have, some of the geometrical ideas, to this context of infinite dimensional vectors. And one of the very useful ideas that we have in the context of vectors is the idea of a dot product. How do we take the dot product of two vectors in two dimensional space? So, let us recall. So, suppose for example, we choose a pair of orthogonal coordinates. So, we have u1 cap and u2 cap as we did some time ago, orthogonal to one another, perpendicular to one another. And we have two vectors. Let us call them E1, which has the coordinates E11 and E12. So, E1 is E11 u cap u1 cap plus E12 u2 cap, and similarly E2 as a vector has the coordinates E21 u1 cap plus E22 u2 cap. Then the dot product of E1 and E2, E1 dot E2 as we write it, is essentially E11 E21 plus E12 E22. So, it is the sum of products of corresponding coordinates. Two dimensions, easy enough to understand. 3 dimensions, easy to extend. In fact, n dimensions, equally easy to extend. Suppose we had two n dimensional vectors characterized by coordinates, say E11 to E1n. So, you have two n dimensional vectors. E1 characterized by coordinates E11, E12 up to E1n, and similarly E2 characterized by the coordinates E21, E22 up to E2n. Then of course, E1 dot E2 is easy to express if we generalize this. It is essentially summation k from 1 to n E1k times E2k. So, dot product generalized to n dimensions. Of course, we assume these are orthogonal coordinates. Now, we can even take this to infinite dimensions. So, we can think of the dot product of two sequences, let us say x1 and x2. So, we have here for example, two sequences x1n and x2n defined over the set of integers n over all the integers. Their so called dot product or inner product, as the formal name is. So, you see, instead of dot product now, we would like to use the term inner product to generalize, and we denote the inner product this way. For the moment, let us assume these are real sequences. For the moment, in that case, if we generalize, it is easy to see that the inner product of x1 and x2 is simply summation on n running from all the way from minus to plus infinity, x1n times x2n. And of course, it is clear that the dot product or the inner product, as we are going to call it in this generalized situation, is commutative. That means, if I interchange the roles of x1 and x2, the result does not change. However, we would like this inner product or dot product notion to give us some of the powers and some of the conveniences that the dot product offers in the context of vectors. One so called convenience or one so called interpretation or meaning that we derive from the dot product is the notion of magnitude. So, in fact, one could think of the notion of magnitude as induced from a dot product if one desires, or in other words, one could calculate the magnitude of a vector by using the notion of a dot product as one path towards the calculation of magnitude. Incidentally, the word magnitude of vectors is used for small dimensional vectors like 2 and 3 dimensional. But when we go to these generalized situations of n dimensional vectors or countably infinite dimensional vectors, we replace the word magnitude by the word norm. So, we say that we would like the squared norm of x to be the dot product of x with x, as is the case with vectors. So, if you recall, a dot a, where a is a vector in 2 or 3 dimensions for that matter, is the magnitude squared of a. The same should hold good here. When we take the dot product of a sequence with itself, it should give us the squared norm of that sequence, where norm is a more general word for the magnitude. In fact, in L2R, the norm is representative of the energy, but at this moment we are not talking about L2R, because we have not yet come to the situation where we are dealing with functions of continuous variables. So, we will postpone that interpretation for a minute, not very far away from now, and once again come back to sequences. Even for sequences, when we take the dot product of a real sequence with itself, we indeed get something that we liken to an energy of the sequence. So, it is not uncommon to refer to the dot product of a real sequence, or for that matter sequence with itself, as the energy in that sequence. Anyway, I kept emphasizing real for a good reason. When we talk about the magnitude of a vector, or for that matter the more generalized word norm, what is it that we expect of a magnitude? We want the magnitude or the norm to be a non-negative number, and in fact strictly positive if that vector is non-zero. So, there are the following things that we demand of this concept of norm or magnitude. Let us write them down. This is a useful and a powerful idea to have around us. So, what do we want of a norm? So, if I have a vector x, essentially a sequence x n, n over the set of integers, then its norm, which we shall denote in the following way, we will denote it like this, should be essentially the dot product of x with x square root, and further would want norm of x to be non-negative, and if at all the norm of x is 0, that implies and is implied by the sequence itself being 0 everywhere. That is, x of n is equal to 0 for all n belonging to the set of integers. This is important. So, we do not want that norm to be 0 unless the sequence itself is the 0 sequence. A non-zero sequence, even if it is non-zero at one point, must have a non-zero norm, and a 0 sequence must have a 0 norm. Does our dot product satisfy this? Well, for real sequences it does. If x n is real, or rather if x 1, x 2 are real, and we take the following definition, the dot product of x 1 and x 2 is essentially summation on n going from minus to plus infinity x 1 n, x 2 n, then the dot product of x with x is essentially summation n running from minus to plus infinity x squared n, and as long as x n is real for all n belonging to z, this is this satisfies the requirements of norm. It is non-negative and it is 0 if and only if the sequence is identically 0. But what if this is complex? So, we have to allow complex sequences too. One of the coordinates could be complex, and in fact, the situation could be such that x squared n could be plus 1 for one of the coordinates and minus 1 for some other coordinate in that case, because when you square a complex number, nothing guarantees the output is going to be non-negative. In fact, nothing even guarantees the output is going to be real. Where is the question of non-negative? So, this definition is not going to work when x 1 and x 2 are complex sequences in general, and we need to tweak the definition a little. Well, it is not that difficult. After all, what we want is that for every coordinate you must get a non-negative quantity when you take point by point products. So, all that we need to do for that purpose is to complex conjugate the second argument in that summation. So, the small change for complex sequences will do our job. Dot product of x 1 with x 2 is summation over all n x 1 n x 2 bar n, where bar denotes the complex conjugate. Now, one point to note here when we make this little change is that commutativity property is lost. So, if I take the inner product x 1 with x 2 and then if I take the inner product x 2 with x 1, there is a complex conjugate relationship. And this is the more general requirement of a dot product. In fact, this is the simplest way in which one can define a dot product between sequences. There are many other ways, again an infinite number of ways. but at this moment we shall not go into the other ways, they will only confuse us. This is what is called the standard inner product, but one can have many other non-standard inner products which obey the following conditions. The first condition is this, that we write down here. The inner product of x 1 with x 2 is the complex conjugate of the inner product of x 2 with x 1. Secondly, the inner product is linear in the first argument. In other words, if I take a 1 x 1 plus a 2 x 2, where in general a 1 and a 2 could be complex, and take the inner product with x 3, it is essentially a 1 times the inner product of x 1 with x 3 plus a 2 times the inner product of x 2 with x 3. This is the second requirement of an inner product, linearity in the first argument. The third requirement of the inner product is what we have been building towards all this while, namely what is called the positivity or non-negativity. In fact, positivity is more appropriate. Positive definiteness, namely the inner product of x with x is always greater than or equal to 0, and x equal to 0 implies and is implied by the inner product of x with x being 0. In fact, any operation between two sequences x 1 and x 2 which obeys these three conditions is called an inner product, and the standard inner product that we have just described is one such, which we shall use very frequently. So, in the discussions henceforth, when we say inner product of sequences, we mean the standard inner product unless otherwise specified. All right. So, let us just verify this for completeness. Let us verify this for the standard inner product. The inner product of two sequences x 1 x 2 is essentially the sum n going from minus to plus infinity x 1 n x 2 bar n. Definition. The first property, as we said, is complex conjugate, easy to verify. So, in fact, I will leave it to you as an exercise. Verify the properties of what is called conjugate commutativity, the first property. And linearity. Linearity in the first argument. I leave it as an exercise, easy enough to do. But we shall, because it is so important, verify the third property, the positive definiteness. Indeed, if we take the dot product of x with x, it is summation n going from minus to plus infinity x n bar, which is summation n going from minus to plus infinity mod x n squared. And it is very easy to see that this is equal to 0 if and only if x n equal to 0 for all n. Even if one of the coordinates is non-zero, that particular mod x n squared is going to be non-zero and it is going to contribute a positive term. And of course, it is very easy to see that each term for every n is strictly positive if x n is non-zero. So far so good. So, now we have built up the idea of inner product or dot product between two sequences, which is going to be useful to us. So, we have moved from 2 dimensional to 3 dimensional to n dimensional, n is finite, and then to countably infinite dimension. Now, let us move to uncountably infinite dimension. So, suppose I take a function of the continuous variable t. How can I extend these notions? So, extension to uncountably infinite dimension. Well, this is going to be very difficult in general, but very easy in particular if we simply accept that every t for real t is a different dimension. Simple. So, if you have a function x of t, t over the real numbers, x of t for a particular t is the tth coordinate, so to speak. And there is an uncountably infinite number of such coordinates indexed by the real numbers. So, in principle, in a given function you have complete liberty to put down the value of x t at every different point t. The only catch is we have agreed that we would like to make the function square integrable. So, that does put some restriction on x t, but not a very serious one even so. Now, dealing with infinite dimensional spaces, if we wish to do it very rigorously and very carefully and to satisfy the fastidious mathematician is a difficult job, and we do not really intend to do that all the way in this course. If some of us do wish to take that puritanical perspective, one of course would benefit from it in some ways, and one could look up a book on functional analysis. But what we wish to do is rather to give intuitive understanding of some of the concepts at different places. The intuitive understanding will not be different from a more rigorous understanding for those specific situations, but it may not quite be complete. Even so, we would not suffer too much in our study of wavelets, in our applications of wavelets, if we take this intuitive path to some extent, not all the time. I mean to some extent in the context of dealing with infinite dimensional spaces. So, with that little prelude, let us come back to this uncountably infinite dimensional space of functions on the real line, in which case we can generalize. So, we can generalize the notion of a dot product or inner product. Between two functions. Essentially, if I take two functions x and y both on the variable t, that dot product is not going to be a summation anymore, but an integral. So, x t y bar t dt. Taking that idea further of multiplying corresponding coordinates, and instead of summing you now integrate. So, the integral replaces the operation of summation here. Now, of course, it is easy to verify, and I leave that as an exercise to you, the properties of linearity and the commutativity and so on. So, I leave it to you as an exercise here. Verify the properties of conjugate commutativity in other words, if I interchange the order of the arguments, there is a complex conjugation involved. Second, of linearity in the first argument. So, if I take a linear combination of two vectors or two functions in the first argument, then the corresponding inner products are also similarly linearly combined. And third, positive definiteness. So, I leave this to you as an exercise. But what I wish to emphasize at this point is the famed Parseval's theorem, of which we are aware in the context of the Fourier transform. So, let me recapitulate that very important theorem in the context of the Fourier transform, and let us also give an interpretation to it. You see, the Parseval's theorem as we know it for continuous functions says that if x t has the Fourier transform, now I am going to use the frequency Hertz frequency variable. So, this is the Hertz frequency variable nu. In other words, what I mean by that is that the Fourier transform of x t is essentially integral x t e raised to the power j 2 pi nu t dt integrated over all time t. So, this is the Hertz frequency variable in Hertz. Recall that you can also have an angular frequency variable. So, for example, you could write x cap of omega. Now, I will use this capital omega when we are talking about continuous time. We are going to follow some notions of different notation for continuous time and discrete time. So, we will use this as the angular frequency variable for continuous time. In which case x cap omega is x of t e raised to the power minus j omega t dt, and there is a simple relation between capital omega and mu. Omega is 2 pi nu, angular frequency and Hertz frequency. Well, simple things, but we should put down all our cards in the beginning, so we do not get confused later. Now, again, this is a little bit of abuse of notation, because I am using x cap of capital omega here and I am using x cap of nu there, and depending on the context I must interpret either Hertz frequency in the argument or angular frequency in radians per second in the argument. Normally, from the context it shall be clear, and if there is some confusion likely, we will make it clear by explicit statement. But remember that from the context we should be clear whether we are dealing with Hertz frequency or angular frequency, radians per second. Anyway, with these details, let us come back to the Parseval's theorem. What does the Parseval's theorem say? The Parseval's theorem says the following: if you have the Fourier transforms of x and y, so if x t has the Fourier transform, let us use the Hertz frequency variable x cap nu. and y t has the Fourier transform y cap nu. This arrow denotes the Fourier transform. Then there is an equivalence of the Fourier transform inner product and the time inner product. That is what the Parsifal's theorem says in our language now. So, the inner product in time, so to speak, is equal to the inner product in frequency. In other words, if you take x cap and y cap and construct their inner product in the same way, treating the frequency as the independent variable or the argument. Now, this is a very beautiful and a very powerful interpretation of the Parsifal's theorem. When we talk about the inner product perspective, we have a very different way of looking at Parsifal's theorem. And in fact, if we really think of it a little more deeply, Parsifal's theorem becomes so much more intuitive when we talk in terms of inner products. And let me take a minute now to show you why it is so intuitive. Indeed, what Parsifal's theorem says in the language of inner products is this, and let us do the same in 2 dimensions, and then it will be absolutely amply clear. So, I have 2 vectors, let us call them x and y. Now, what Parsifal's theorem says is x dot y is independent of the coordinate system, simple enough. What coordinate system we choose to represent x and y does not affect the inner product. That is what Parsifal's theorem says in a way. And to strengthen, you see, it may not be obvious to you why Parsifal's theorem relates to this statement. It is obvious for 2 dimensional vectors that the inner product is, or the dot product is independent of the coordinate system. What is not obvious is why is this related to the Parsifal's theorem? Well, towards that we need to go back to what x cap nu really is in a way, and that will become clear if we write down the inverse Fourier transform. So, we can write down x t in terms of the inverse Fourier transform as x cap nu e raised to the power j nu t d nu. Nu is the Hertz frequency variable again. So, in a way what we are saying is we are reconstructing x t from its components. Each of the x cap nu for different values of nu is a component here, and this is the way we have reconstructed x t from its components. And in reconstruction we have used these vectors. Each of the e raised to the power j nu t is like a vector, is a function of the real axis. The only catch is e raised to the power j nu t is not an L2R function. So, we have to deviate a little bit there from our discussion, but if we choose to ignore that fact, we have essentially taken these coordinates, multiplied them by the corresponding so called functions along each of the coordinates nu and added them to get the function x t. So, each of the x cap nu is like a different expression of the same vector x in a different coordinate system. So, what we are saying in Parsifal's theorem is that the dot product is independent of the coordinate system. Whether we choose to use the standard coordinate system of time to represent the function or the slightly less obvious coordinate system of frequency to represent the same function, the dot product remains the same. So, these and some other such interpretations are what are offered when we represent functions in terms of vectors, or when we think of functions as generalizations of the ideas of vectors. And now, for the last remark in this lecture, which we shall build on even greater in depth in the next, namely, what is the connection between functions and sequences, continuous functions and sequences. Just to initiate the discussion here without completing it or rather taking it further, we shall do in the next lecture. But just to initiate the discussion, let us go back to the idea of piecewise constant approximation. So, suppose we have this piecewise constant approximation of this function on intervals of length 1. So, I take the standard unit intervals and I make a piecewise constant representation of a function. So, I have this. So, let the values be, let us say, c minus 1 here, c 0 there, c 1 there, and so on and so forth. Now, it is very easy to see that if I take the basic function phi t described this way, 1 between 0 and 1 and 0 elsewhere, then this piecewise constant representation can be written as c minus 1 among other terms phi t plus 1 plus c 0 phi t plus c 1 phi t minus 1 and what have you afterwards. So, to conclude just this introduction of this correspondence, we can note that equivalent to this piecewise constant representation that I have here, this function in V 0 that we talked about last time, equivalent to that function is the set of values c minus 1, c 0, c 1 and so on. So, the sequence c n over all the integers is equivalent to that piecewise constant function in V 0. Any of them can be constructed from the other. From that piecewise constant function, we can construct the sequence. From the sequence, we can construct the piecewise constant function given phi t. Now, this equivalence is what we shall take further and delve into deeper in the next lecture. And in the next lecture, we shall also build further these ideas of vectors, functions and sequences. Thank you.